Hi, welcome. I hope you've enjoyed the conference so far. I want to wrap up today by talking about some fairly broad topics. I want to talk about software engineering. I've got interested in the things that I think are durable in our profession. We think of ourselves as an industry that's fast moving, and it is. But I think that there are some foundational ideas that are deeper than some of those things that we tend to spend a lot of time thinking about. And I think that some of these principles are what really underpin our ability to build better software faster. So I'm just going to share my screen and get to my presentation. Hopefully you can see my presentation on the screen now. So this is what I want to talk about for today. So modern software engineering, how do we get to be able to build better software faster? And I think we're learning how to do that and how to do that better. So my agenda for today is to talk about what really is engineering and what are these common foundational principles that are going to give us a better chance of success. And I want to talk about 10 guiding principles that I think define what engineering for software ought to really be, and then think a little bit about applying these guidelines. So what is engineering? And I think that we often confuse that when we think about it. In other disciplines, certainly modern engineering is just the stuff that works. You know, if it doesn't work, we change it. We find a better way of doing things. And the idea of engineering is to guide us towards better chances of success. Software is difficult stuff. So what's the stuff that works for us in that kind of context? Now, I've been thinking about these kinds of ideas for a long time, and one of the weird side effects of that is that I get involved in quite a lot of conversations about bridges, because what nearly always happens to me, somebody comes and says, yes, but software development isn't bridge building. Well, no, it's not. But I think often what we think of as bridge building isn't really what engineering is about or what bridge building is about either. One of the attributes of engineering is that it's different in different contexts. Bridge building is not the same as automotive engineering. It's not the same as chemical engineering. It's not the same as aerospace engineering. All of these things have different attributes, but they share some common ideas. So I want to pick out some examples from these particular fields of endeavor, and I'm probably going to mention Lego along the way as well in talking about the concepts of engineering that I want to talk about. So what does this stuff really mean for us? So we can start off by thinking about what engineering as a word means. And my preferred definition, at least in the context of software development, is this. It's the application of empirical scientific approach to finding efficient solutions to practical problems. I think it's fair that that wasn't always what we'd use as a definition for engineering. The word comes from building siege engines and stuff like that in the Middle Ages. But I think this is what modern engineering is about. It's like the practical arm of science, really. We're using scientific style reasoning to solve important problems. And this is important stuff because in reality, this is how we solve the hard problems, whatever they might be. These are all forms of engineering. We're engineering vaccines to be able to cure us of COVID. We're engineering space rockets and the telecommunication system. And all of these things are the fruits of engineering. This is how we as a species do the hard things. To put it more simply still, I would argue that this is actually the foundation on which our culture is built. Certainly for the last 300 or 400 years, this is how we have made progress. And that you can graph that in a fairly profound terms. For much of our history, progress was enormously slow, certainly in terms of technological advancement. And it's going slowly all the way until we start to get up to around the 1600s, and then something happens, something kicks off, and it explodes exponentially at this point. This is the point, roughly, in history when science was invented. So this practical application of science to solving problems is really what I'm talking about. Here's another exponential graph. This is based on the work of Buckminster Fuller originally, who came up with this idea of how rapidly knowledge doubles globally. And the estimates were that in 1900, knowledge, the whole of human knowledge, doubled every century. And by 1945, knowledge was doubling every 25 years. By 1982, knowledge, the estimate was that human knowledge was doubling every 12 to 13 months. There are some predictions which sound a little bit extravagant, but that says that IBM predicts that knowledge will be doubling by 2020. Before 2020, they predicted that it would be doubling every 11 to 12 hours. I think that's probably a little bit extravagant, but nevertheless, something important is going on here. So science was invented back there somewhere, and this is where computers and software started to kick in. So we are at the root of this explosion of knowledge, really. So what's engineering as a discipline really for? I think that we think about it as being predictable and a cookie cutter process, but it's not that really. What engineering is really for, it's not to define perfect solutions. What it is really for is to eliminate the stupid solutions, rule out the bad ideas. And that's what it is that we're trying to achieve. So we think of it often in terms like these, of these sorts of cookie cutter productions, but I think that's because we are the products of an industrialized society. And this is what industrialization looks like, this manufacturing process. But this is not the engineering. The engineering went into solving the problem of how to regularize these processes. This is not our problem. This is production. This is manufacture. This is not engineering, certainly not in our terms. So this is never our problem. And I think we've suffered from assuming that it was. One of the things that, when you think about software, makes our discipline fairly unique is this. We come up with some ideas, some designs that we capture in the form of code. We turn those ideas into an executable form, a stream of bytes. And the unique thing here in terms of digital assets, the things that we create this crystallization of ideas, is that we can recreate that stream of bytes perfectly, essentially for marginal or close to zero cost. We can just simply press the button and copy the stream of bytes as many times as we like. So production for us is free. Our problem is entirely different to the manufacture of physical things. And yet, historically, we've tended to apply manufacture style thinking to the production of software. So I would say that fundamentally, the kind of engineering that I'm talking about here is about exploration and discovery. It's certainly not about cookie cutter reproduction. We are always doing something new, because if production is free, then why would we do otherwise? If we can recreate a system for essentially no cost, why on earth would we spend lots of money and time and effort building something else? We wouldn't, unless there was something new about it, at least in the context with which we're creating it, not necessarily globally new. So I would argue that software development is fundamentally always about exploration and discovery. We're exploring the problem to understand it better. We're coming up with solutions to the problem that we're exploring. We're trying to hone in on what our users need and what they want. And we're trying to do that in our commercial environments that are constrained and so on. So we're always kind of hunting around for these solutions, and that's fundamentally, deeply, profoundly at the roots of our discipline. So if that's true, then we should be optimizing for learning. Our profession should be focused significantly on focusing on learning. And we should also be looking to manage complexity, because we build hugely complex systems. And one of the things that we want from those systems is our ability, as we learn new things, we'd like to be able to cope with our learning and add to the systems that we're building. So we need to maintain our ability to change our systems. And for that, we need to design systems that are capable of growing and changing over time. It's very unusual to build a system and then walk away from it and it to carry on working without some kind of changes and adjustments to fit into its context, whatever that might mean. So if we want to optimize for learning, I would argue that there are 5 things that we need to focus on. So first, we need to be iterative. Then we need to be feedback driven and incremental, experimental and empirical. And I'd like to explore each of these ideas in a bit more detail. So let's start off talking about iteration. And let's look at an example from the aviation industry. This is the Wright Flyer. This is the first controlled powered aircraft. I'm being specific because there were other innovators that came before that did solve different parts of the problem, but the Wright brothers brought it together and were able to build this thing. Now, these things at this stage and for a couple of decades afterwards, these things were death traps. They were incredibly dangerous. The original pioneers in aviation, many of them lost their lives in aircraft that they constructed. And we might think of this as more like a work of craft. It looks a bit basic in these terms, but actually the Wright brothers were fairly sophisticated engineers. Amongst other things, they used techniques like they built the first wind tunnels to be able to evaluate models of wings and so on. And they did stress calculations and all these sort of things. So this was an engineering discipline. As aviation developed, we built more sophisticated machines, and as we learned more and these things became safe enough that aviation could start moving paying passengers around without them taking their lives into their hands. And then we get to modern aircraft. In 2017, commercial aviation flew the equivalent of 2/3 of the population of the planet. And they did that with no fatalities. That's the first time that that happened. And this is how engineering makes progress. Now, this happened as a result of lots of people being hurt and being killed in accidents and learning from those mistakes. Aviation had built a safety discipline that learned from, investigated each accident and took those learnings and applied it going forwards. So this is an iterative approach. It's a very slow iterative approach, but now, as a result of all of this learning over a long period of time, over 100 years, we've refined and refined and refined aircraft until if you're sat in one of a modern aircraft, you are statistically safer than you are sat in the room where you're sat right now. That's a remarkable thing. Iteration is a remarkable idea. At first, it seems a bit ad hoc, but it's not. It's much stronger. One of the powers of iteration is that whatever our starting point and whatever our goal, we can hit the goal with a few tricks if we use iteration. So what we need is that we need a measuring stick of some kind of fitness function that determines whether we're moving closer towards the goal or further away from it. And as long as we have that, we can hit the goal, because now we can start iterating. So we can just go off in random directions, and then we can measure whether we get closer to the goal or further, and we can discard the steps that take us further away and prefer the steps that move us closer. And over time, step by step by step, we can hit the goal. And we can do that as much as we like, and we can even do that if we move the goal. If we move the goal, as long as we change the fitness function, we can hit the goal. This is remarkable. The next in my series of 5 things that are about optimizing for learning is feedback, and using feedback to help us understand where we are. I'm trying to think about and apply these as sort of engineering scientifically based principles. So feedback is a tool that we can use. Feedback in this instance is this measurement that we take to determine against our fitness function whether we're closer or further from our goal. And this can take all sorts of different ways. And once again, this sounds a little bit ad hoc. It sounds a little bit like we're not being diligent enough and we're not planning enough. But that's not the case. This is the more profound, more correct way of solving problems. Let's imagine that we're tasked with balancing a broom. And how do you go about doing that? Well, we could take a kind of waterfall approach to balancing a broom if we wanted to. We could kind of figure out where the center of mass of our broom was, and we could kind of work out that. And we know that in order to balance something, we've got to line up the point of contact, the force of gravity with the center of mass, and so we could rotate the broom until it's in the right place, and so on. And essentially, to solve this problem, there's one correct answer. We've got to precisely identify exactly the right point of contact, and we've got to position the broom just perfectly with no impulse left that leaves it moving one way or another that's likely to result in it tipping, because this is more likely to happen. There's only really one solution to this, and we're very, very unlikely to be able to hit that solution. The alternative, which I'm sure is what went through all of your minds when I talked about balancing a broom, is this. We don't do any of that stuff. What we do is that we get the broom, we put it on our hands, and we start wobbling our hand around. This is feedback driven. And the faster we go with the feedback, the more precise our control can be. If we're moving our hand very quickly, we can make very tiny movements. If we're very careful about how we sense what's going on, we can be very, very precise in doing this. But also, if I was balancing a broom on my hand and you came and pushed me, I could take a few steps and I could do a big move and I could keep the broom balanced. This is a much more dynamic approach, and this is a much more scientifically valid approach. In fact, this is how space rockets fly. Space rockets fly on exactly this principle. They use feedback and sensing the direction of the rocket, the tilt of the rocket, and then they control the thrust in the same way that we would move our hands to balance a broom, to balance the rocket on the thrust of the engines. Next in my list is incremental. Incrementalism is about building systems step by step. This is one of the first components of the International Space Station. Over time, these things were launched into space and assembled until we end up with what is one of the most complex physical devices that humans have built. The internet makes this pale into insignificance, to be honest, and quite a lot of software systems. But in terms of physical devices, this is the most complicated machine that we've built so far. And we do that incrementally. That's how we solve hard problems. We do them step by step by step. We evolve systems towards better solutions. And part of that process of evolution is being experimental, trying ideas out. When I talk to people about being experimental, often this sounds like a fairly scary idea. But actually, once again, this is how we always proceed. And fundamentally, we must take those kinds of risks. We know we make mistakes, and we need to allow ourselves to make mistakes. So being experimental allows us to make those mistakes in controlled circumstances, understand quickly and early that we've made a mistake, and correct it. So to do that kind of thing, we need to take control of the variables. We need to be very thoughtful about the way in which our system can change, so that we understand when we're carrying out an experiment what's happening. One of the examples that I would place in your mind for that in terms of software is an automated test. An automated test is a very powerful form of experiment. And to have a successful automated test, we'd like to control the variables so that largely there's one reason for that test to fail, and then we've got a good experiment and we understand the impact of our changes on that piece of behavior. Here's another example from the aviation industry. There's been a very long-standing approach to the way in which you make progress in aviation. If you want to create a new aircraft, the idea in aviation is that you never fly a new engine with a new airframe. So what you do is that you start off with an old airframe and you take the engine off and you put the new engine onto the old aeroplane, and then you go and fly that. Some test pilot goes and tries it out and see how that works. And then if all that looks okay, then you get the new airframe and you bolt the old engine onto it, and you go, and the test pilot goes and flies that. And then when all of that looks happy and safe and you haven't killed too many test pilots, then you bolt all of the new pieces together and you go and fly that. That's how progress is made. We try stuff out. We don't assume that we're going to be perfect. This is not, although modern aircraft design is deeply supported by software simulations and so on, and engineering models, we still go and fly the aeroplane. We still go and try it out because we're going to get stuff wrong. So being experimental isn't admitting defeat. This is how we make progress safely and optimizing for our learning. The last in my list of 5 is being empirical. And the idea of being empirical is we want to try stuff out in the real world. Sticking with my aviation theme, this is one of the first ever jet aeroplanes. This was a German aeroplane built during the Second World War. It's called a Heinkel. And you can see that this doesn't look very much like a modern jet aeroplane. They tried the stuff with putting an engine, an old engine on the front of this first, a propeller engine, and they went and flew it to try out the aeroplane, and then they fitted the jet engine and went it flying. But the noticeable thing about this is the organization of the undercarriage, the wheels that are contacting the ground. This is what's called in flying circles a tail dragger, because the tail is down at the back and there's a little wheel at the back, and the main wheels are ahead of the center of gravity. Now, this design was really good for aeroplanes with big propellers on the front, but a jet doesn't have a big propeller. And so they built this thing, they tried it out with the propeller first, it went and flew, and then they put the jet engine in, and when they test flew this, they melted the runway because the jet blast is facing down at the runway. So they destroyed the runway, and then they learned. So nearly all modern jet aeroplanes now have a little wheel at the front, and the main wheel's a little bit further back. So it sits flat. It's not tilted back like this. That's empirical learning. You try stuff out, you find out what works, you discard the stuff that doesn't, and you prefer the stuff that does. You're at an agile conference. Inspect and adapt, anyone? This is how science works. This is how engineering makes progress. We're still doing this in this kind of empirical learning. SpaceX is in the process of trying to build humanity's first totally reusable spacecraft. It's called the Starship, and they're blowing them up on a regular basis. They blew one up last week, trying to get into orbit, and it didn't work. But this is how you learn. You try stuff out, you do all of the calculations, you make your best guess about the design, and then you try out the ideas in safe, controlled circumstances. And at each step, you learn. The complexity of the systems that we deal with is growing enormously. This picture in the middle with Amazon on the label is a diagram. This is actually part of an animation. There's an animated version of this because this is dynamic. These are just the microservices in the Amazon ecosystem. This is complex stuff. And in order to be able to manage these kinds of systems, we need to worry about that and take that stuff into consideration. So modern software is often complex. And so in order to be able to give ourselves better chances of success, we need to not only focus on the learning, but also on the management of that complexity. And for that, I have another 5 things. So we can talk about modularity, separation of concerns, abstraction, cohesion, and coupling. Let's start with modularity. And here's an example of modularity, still with my aviation theme so far. So aircraft are often modular systems. Most engineered systems are are modular systems. You can take out parts, you can change the wheel on your car without throwing your car away, you can change the engine in a car, you can change the engine in an aircraft like this. This gives us a lot of capability, gives us more flexibility in terms of design. It allows us to upgrade things like the engines in this jetliner and replace them with newer, more fuel-efficient ones over time, or to carry out maintenance on these sorts of things. This is true of what seem like deeply integrated devices too. Here's a modern phone, an iPhone that's kind of separated out into some of its pieces. These are deeply designed to work together, but they are still discrete modular components. Each part of this system has a different function and is focused on a different part of the problem. A more prosaic example, perhaps, the closer to home, is the idea of printer drivers. When I first started writing software on early versions of PCs, then if you wanted to print something out on a printer, you had to know exactly what printer was connected to your computer, and you had to write to the protocol that printer supported, because there wasn't the idea of printer drivers supported by operating systems. So the idea of a printer driver is an example of modularity. So what we do is that we come up with an abstraction that we can talk to that just kind of abstracts the problem of printing from us, and then we can plug in a module that deals with the distinct protocol that a particular printer understands and use that. Here's some code that's kind of less than modular, and just look at sort of the impact on this. This is some C code, and it's fairly unpleasant. There's 361 lines in an if statement in this. The most common feedback that I get when I show people this is, oh, we have functions that are much longer than that. But here's what this looks like, and let's just think if we could just improve this code by applying modularity. Well, fairly easily, actually. So this block that I've highlighted here is inside an if statement, and it's not very clear what's going on. If unlikely bang CI do something else, fairly ugly, nasty code. Well, actually, I think that what's actually going on is more like this. If there's no connection, create a connection. And I think that's it. So if we were to do that, we could just improve the modularity of that code in a single step. And I think you would all agree that this code is now better as a result of that simple change. My favorite description of good design is from Kent Beck. Good design is about moving the things that are related closer together and the things that aren't related further apart. I think that's a pretty good summary of what we're talking about. So moving the things that aren't related further apart is really what modularity is about. And moving things that are related closer together is really what cohesion is about. And I think that, it doesn't really matter what the nature of the software is. It doesn't matter whether you're talking about an object-oriented system or a procedural system or a functional system. Modularity and cohesion are still the hallmarks of high-quality code. Let's look at the next in my list, separation of concerns. This is a modern BMW car, and BMW have decided to take an interesting step. A lot of manufacturers are taking very similar steps. What they've decided is they're going to separate the concerns of the utility of the vehicle from the mechanism of transport. So they divide for electric cars at least, they're having a platform with the motors and the batteries and the steering mechanisms and so on. And then all of their cars are going to share that same platform. So we could use this same thing for an SUV, for a saloon, for a sports car, and so on. And that separation of concerns gives a huge amount of flexibility in terms of the design of the system. Here's another car to demonstrate the ideas of abstraction. This is obviously a slightly different kind of car from a while ago. It's a beautiful kind of looking machine, but it's interesting. One of the things about this is there's not an awful lot of abstraction going on here. You can kind of see the mechanism in place. There's this bit here. This is, I understand, I think, is a mix of the throttle and the brake in one control. So they hadn't really thought about abstracting the controls very much here. And this thing here, this is the tiller. This is the thing that is the steering. And you can see, you can kind of see how that works. It's connected to this tube here. We move this handle and that moves this. And there's a little push rod here that's connected to the front wheel and steers the front wheel. There's not an awful lot of abstraction going on here. But think about how cars evolve. So we started off by coming up with, controls. This is still not modern. There's still some weird looking things here, but we've now got this steering wheel. And, we evolved those over time until we get to the steering wheel in a modern car. So let's just think about how that works. Could you imagine can you tell from this picture how this steering wheel works? No, you can't. So it might be conventional kind of parallelogram steering or rack and pinion steering, or it might be something like this, power-assisted steering of some kind, or it might be wholly electrical. And you can't tell because we've abstracted the problem. We've abstracted the problem completely of how this thing works from how we use it, how we interact with it. And that's a fundamental strategy in engineering. Let's just kind of contextualize that in terms of software. So here's two pieces of software and they're talking to each other and they're being incredibly chatty. This is not very abstract. I've got this nasty back channel here just to make you feel queasy of this, breaking the encapsulation of this thing and talking direct to the data store here. Very nasty. This is not good abstraction and not good design. So we could improve the design by abstracting the conversation. So now we could say, okay, we're placing an order and we're going to respond with order placed. This is clearer what's going on. This is easier for us to isolate these parts of the system and allow us to make progress in each part of the system. If we're able to keep secrets like this through abstraction, once again, it means our code is better. It means that we can make progress more easily. We can use other parts of systems and reuse them more easily. And then there's coupling. I said there'd be Lego. So these are two different versions of Lego, two different Lego kits. When I was a kid, the Lego on the right-hand side of the screen was what we had, and my granddaughters still have great pleasure making things out of these things. These are effectively just generic building blocks. So my granddaughters build things, and you say, "Oh, look, that's lovely. What is it?" And they say, "Oh, it's a giraffe." And you say, "Oh, yeah, wonderful, exactly like a giraffe." But it might also look like a spaceship, as far as you're concerned. It gives us complete flexibility. And then there's this kind of thing. This is a different kind of system. This is a much more coupled system. There's kind of one right way to put all of this together to end up with this car. So this is very flexible and very generic. This is very precise. Now, there's no one right answer here. Sometimes you want the car on the left, sometimes you want the generality on the right. So managing the coupling is important, but there are trade-offs here. The coupling on the left is very high. And so if I lose one piece here, I've really kind of compromised my ability to build this thing. I can't build a submarine out of this kit because all the pieces are wrong. But I can build whatever I like. I can build cars or submarines or giraffes out of the kit on the right. So coupling matters and is a design choice and is part of our engineering decision-making. Let's look at that with our services or components of our system once again. So let's imagine that we've got version 2 now of the orange service. And we had all of this interactive stuff here, and there's a delivery date that was in the middle of here. We changed the format here in this implementation, and that's broken that. But because we had the back end, we talked to the database, it's broken that as well. So now we've destroyed our system through overcoupled systems. What we could have done instead is we could have used the less coupled version. So we could have decided to keep secrets. We could even put some little adapter on front of our orange service here to manage the coupling. So now when we place an order, we could say this order has been placed with version 1 of our protocol. So we've got version 2 is the internal representation, but our little translator can translate and return version 1 of the date. So we've decoupled these two pieces of software, and once again, we've ended up with better systems. I haven't said anything about the language that these are implemented in, or the technology, or the problem that they're solving, really, other than this kind of generally abstract idea of placing orders. But this idea is deeply important if we want to be able to build complex systems. So we've kind of come up with these 10 things. Optimizing for learning, about iteration, feedback, incremental and empirical, experimental and empirical learning, and optimizing to manage complexity, modularity, cohesion, separation of concerns, abstraction, and coupling. These things matter for one reason, really, and only one. They allow us to change our software. I would argue that our ability to change our software as we learn new things is the defining characteristic of quality for software. It's not that other things aren't important. They are important, but they are consequent on our ability to change the software. If we want our software to be scalable or secure or resilient or to have new features, we can't do that unless we can change our software. If we start off with perfectly secure software, it won't be secure for long because the environment will change. Hackers will learn new ways to exploit our software. So we still need to change our software to stay secure. So the ability to change our software, I would argue, is the defining characteristic of quality in software. Change is constant. Change comes from all kinds of different reasons. Requirements change, technologies change, business change, JavaScript change, frameworks change all the time. There is no static. There is no write the code once, be perfectly right, and it's all good, because the world is changing around us. We can't rely on them. And so we must maintain our ability to evolve our software as we learn new things. So the quality of our system is defined by our ability to change it. And an engineering discipline should be organized to allow us to learn new things and then apply those new things by changing our software. Thank you.